There are many ways to skin a cat, but this is our way. The four quantum numbers are derived from Schrödinger's equation. The first one is the shell, represented by the variable n. The shell can go anywhere in whole integer numbers from 1, theoretically, to infinity.
If my car were an electron, it'd be 500 trillion times larger and 2.2 times 10 to the 33rd times more massive. And if that Red Bull can were a nucleus, I would be advancing in energy levels with the farther out I went, and each advancement would take more energy. This would be 1, 2, 3, 4, all the way to infinity!
The second quantum number, L, is the orbital angular momentum quantum number. This value can be 0, 1, 2, 3, theoretically, any number, as long as it does not exceed n minus 1. If we know something about L, we already know something about the energy level n. We are more familiar with a concept called subshells, which we know as S, P, F, and D.
And the angular momentum quantum number of 0, which is the subshell S.
I represent L equals 1, the subshell P.
And I represent L equals 2, which is the subshell B. And if I were the angular momentum quantum number 3, I would be the subshell F.
And now if I am the principal quantum number, that would be one less than the angular momentum quantum number.
Alright, so our third quantum number is called the magnetic quantum number, and it's defined by m sub L. And this may be negative or positive, including 0, and ranging from negative L to positive L. So we can have any range from negative L to negative L plus 1, so on, 0, 1, 2, so on, L minus 1, and including positive L. For an example, we can say L equals 2. And from that, we know that our m sub L is going to be negative 2, negative 1, including 0, remember, 1, and 2. So that means that in a d orbital, because remember L equals 2 means it's a d orbital, that means there are 5 d orbitals in a d subshell.
The last quantum number is m sub s. This can either be plus 1/2 or minus 1/2. Each orbital can have 2 electrons in it. If there is 1 electron in an orbital, it could either be plus 1/2 or minus 1/2. If there are 2 electrons, each electron must have its own sign. So if there are 2, one must be positive and the other one must be negative. Eric and I are 2 electrons in the same orbital. What if the 2 electrons, us, had the same sign, so we were both positive 1/2? What would happen? Let's try that again. Doesn't work. Well, what if I was positive and he was negative? Beautiful. So, as you can see, that's a good analogy. So something that can help us sort all of this out is Pauli's exclusion principle. That states that no one electron can share all of the quantum numbers as another electron. Let's use this in application. If we had the principal quantum number 3, L equaling 2, and m sub s equaling positive 1/2, what are the possible m sub L values? Well, you could have m sub L equaling negative 2, negative 1, 0, 1, or 2. We know this because the rule for m sub L is that it could be negative or positive, the value for L. So it's negative 2, negative 1, 0, 1, or 2. But you could not have 2 electrons sharing 0 as their m sub L value if their n was 3, L was 2, and m sub s equaling positive 1/2. Let's try another one. If our L was 2, our m sub L was also 2, and m sub s was positive 1/2, what are the possible n values? Well, looking at our rules, we could have 3, because L can only be 1 minus n for its maximum value. It could be 4, because L equaling 2 still exists in the principal quantum number 4, and this continues to go on for as high as n is able to go.